Okay. Today again we are continuing with our lessons in mathematics. And what we have for today is sets. Introduction to sets. A set is a collection of things considered together in some way. A collection of things considered together in some way. One may have a set of playing cards, a set of knives, forks, and spoons, or even a set of children in a school. Alternatively, a set is any well-defined collection or list of objects. The objects in a set are called members or elements of the set. We often use capital letters to denote sets and small letters to denote the elements of a set. We write X is an element of A to indicate that X is an element or a member of the set A. If X is not an element of A, we write X. You can see the sign of element of cancelled shows that X is not an element of A. Sign of element cancelled means that X is not an element of A. The set which contains no element is called the empty set. The empty set is denoted by this symbol or this one. If a set has at least one member, then we say that A is a non-empty set. To specify a set needs to be specified. To specify a set, there are essentially two ways to specify a particular set. One method is by listing the members of the set. Listing the members of the set. When the members are listed, they are separated by commas and enclosed in brackets. For example, the set A is equal to, you open the brackets and begin to list the elements, separating them by commas. The elements of this set A are 2, 3, 5, 7. And that is the set of the first 4 positive prime numbers. The first 4 positive prime numbers are 2, 3, 5, and 7. So it forms a set, and it is written in that form. The other method is to state those properties which characterize the members of the set. Using this method, if S is the set of all elements X such that X satisfies property Y, we write S is equal to, in brackets, you write X with these 2 dots such that that's what these 2 dots stand for, such that X satisfies Y. I will give you the elements of that set. In this case, this symbol, 2 dots, 2 vertical dots like this, is read as such that. That's how you read these 2 vertical dots, and can be replaced by a stroke. you can use stroke to replace it. Using this method, the set of the first four positive prime, sorry, let us take this. Using this method, the set of the first four positive prime numbers may be written as A is equal to, you open the bracket now, write X, such that, you see now we are now using stroke in place of such that, but that's interpreted in the same way, such that X is greater than 0 but less than 8. If X assumes a number greater than 0 but less than 8, then you can see that X can take the values of 1, 2, 3, 4, 5, 6, 7. But we are looking for prime numbers. So you can only write 2, 3, 5, and 7. That's why we call them the first four prime numbers. So X is such that X is greater than 0 but less than 8, and X is a prime number. That explains everything very clearly. So that will give you the elements of that set. You see how we mentioned the properties which characterize the members of the set. All these things that are written here, they give us the properties which characterize the members of the set. So these are the two methods we can use to list the elements of a set. I mean, either you list or you write the properties that characterize them. Let us see some further examples. So we are continuing with some more examples. The following sets are used often in mathematics. A, the set n equal to 1, 2, 3, and so on and so forth is called the set of natural numbers or positive integers. B, the set Z is the set, as you can see, going from 0 positively to the right, going from 0 negatively to the left. It's called the set of integers. The set of integers, you have them positively, you have them negatively. They are usually shown on the number line. C, the set Q is the set P over Q, where Q is not equal to 0. Q is not equal to 0 because if Q is 0, you don't need 0. You cannot divide something with nothing. And P and Q are elements of Z. They are from here. This set Q is called the set of rational numbers or fractions. Q prime is the set of irrational numbers. Irrational numbers are numbers that cannot be expressed as P over Q. Of course, Q is equal to 0 and P, Q, elements of Z. Examples of irrational numbers are square root of 2, pi, and square root of 7. You can see that square root of 2 is not an exact figure. It's approximated. Square pi is equally approximated. It's not exact. Square root of 7, approximated. So these are examples of irrational numbers. The set R is called the set of real numbers. The set R, called the set of real numbers, contains all the numbers described above. All the numbers here, all the numbers here, all the numbers here, all the numbers here. They are contained in the set of real numbers. Together with numbers such as root 7, that is called the irrational numbers. So they all form the set of real numbers. It is usual to represent R by a line called the number line. It is usual to represent R by a line called the number line. The number line is a straight line which is assumed to extend indefinitely in both directions. This is an example of number line. It continues to the left, continues to the right. But from what we can see here, it continues positively to the right, negatively to the left. And it is interesting to note that you cannot list the elements of a number line. You cannot. Because if you continue counting this, it is indefinite. It is infinite. You continue counting negatively, it is infinite. So, but we use something like this to illustrate number line. I do hope that we have gained something from what we have explained so far. So I want us to go into finite and infinite sets. Finite and infinite sets. So that is what we are going to look at now. Continuing with finite and infinite sets. A set is finite when we can determine the number of elements in it. The set of prime numbers between 1 and 10 is a finite set because we know the number of elements in it. Let A equal to the set of prime numbers between 1 and 10. Then A is equal to 2, 3, 5, 7. The set of elements 2, 3, 5, 7. That's the set of prime numbers between 1 and 10. You can see that NA is equal to 4. That is, the number of elements in A is 4. The number of elements in the set A is 4. 1, 2, 3, 4. An infinite set is a set which is not finite. You cannot determine the number of elements in it. The set of counting numbers, is an infinite set. The counting never comes to an end. If you are asked to count the set of positive integers, and you begin to count from 1, 2, 3, 4, you keep on counting. You can count for 1 hour, count for the whole day, count for a whole week. You are still counting. You don't get to the end. Let A be equal to the set of the counting numbers. Then the elements of that set will be 1, 2, 3, 4, 5, 6, 7. You keep counting. It is infinite. You cannot count the elements in that set. You cannot. Even in your lifetime, you cannot. That is, you keep counting, keep counting, keep counting. It's only when you give up and you can no longer count. And yet you have not come to the end. It's very interesting. It is an example of an infinite set. You cannot exhaust the elements of the set. The number of elements in the set A is infinite. And you can see how we show it with these 3 dots. Then we go over to subsets. If every element in a set A is contained in another set B, then A is called a subset of B. This is denoted as A. Use this symbol. B. A is contained in B. That's what this means. A is contained in B. It can also be stated that A is contained in B, or B contains A. Again, denoted by B. You see, in this case, we change the size, so we have to change the symbol. A is contained in B. B contains A. You have to change the size, B and A. Use something like that. For example, if the set B is A, B, C, D, E, F, and the set A is A, E, then A clearly is contained in B. I want you to observe that the set of natural numbers is a subset of the set of integers, which in turn is a subset of Q, rational numbers, which happens again to be subset of the real numbers. We have already discussed these sets, but it is interesting to note that this set is a subset of this, and this is a subset of that, and that is a subset of that, which by implication, that is why you are told that this set of real numbers contains all these other ones. That's why you are told that in your notes, that this set of real numbers contains all the other ones. They are inside it. We are still continuing. We are going to continue by discussing the universal set. We are going to look at the universal set. As a matter of fact, I want us to look at not only the universal set. I'm going to look at the complements of a set, equivalent sets, equal sets, to bring us to the end of what we have here. So we continue. We look at the universal set. If A is a subset of a larger set, then the larger set is called a universal set. For example, if we consider the students in your school, in your class, then the universal set will be the students in your school. On the other hand, if we consider the students in your class who sit in the front row. Then the universal set can be your class or your school. The notation for the universal set is usually this type of U or E in this form. So you denote universal set either with this or with that. Complement. The complement of a set is the set of elements outside the given set but are members of the universal set. Let's take it again. The complement of a set is the set of elements outside the given set but are members of the universal set. I think this example will show it. If U is equal to 1, 2, 3, 4, 5 is a universal set, and A equal to 2, 4, you see the elements in A, you see the elements in the universal set, then the complement of A, because you know A is equally inside this universal set, then the complements of A will be the set. See the way you write complement of A prime, A complement. The complement of the set A is written like this, A prime. It is equal to 1, 3, 5. These are elements that are outside the set A, but they are within the universal set. 1, 3, 5 are outside the set A, but they are within the universal set U. Equivalent sets. Two sets are equivalent if they have the same number of elements. Two sets are equivalent if they have the same number of elements. If A is equal to the set of Obi, Joke, and CD, these are the elements of that set A, and B contains, set B contains 1, 2, and 3. Then A is equivalent to B because each of them contains 3 elements. Because NA is equal to NB, that is the number of elements in A is equal to the number of elements in B. Equal sets. Please take your time to understand the difference between equivalent sets and equal sets. Two sets A and B are equal if the number of elements in A is equal to the number of elements in B, and if the elements in A are identical to the elements in B. Either you are talking about names of people, or you are talking about numbers, or you are talking about something that has to be identical. What you have in the two sets must be identical before you consider whether they contain the same number of elements. That is, the two sets. The two sets must contain the same number of elements and identical elements before you can say that they are equal. Unlike in the case of equivalent sets, once they contain the same number of elements, whether they are identical or not, they can be described as being equivalent. Look at the union of sets. The union of two sets A and B form another set written as A union B. This is set A union set B. This is the symbol for union. The union consists of all the elements of A and all the elements of B. For example, if A is the set of students studying mathematics and B is the set of students studying physics, then the union of the sets A and B is the set of all the students studying mathematics or physics or both. Also, if P is equal to the set 1, 2, 3 and Q is equal to the set 2, 3, 4, 5, then P union Q is equal to the set 1, 2, 3 union the set 1, 2, 3, 4, 5. That union is given by the set 1, 2, 3, 4, 5. You will observe that no digit is duplicated. You don't duplicate any digit. You can see that P and Q are subsets of P union Q. That is, P is contained in P union Q and Q is contained in P union Q. Intersection. The intersection of two sets X and Y is written as X intersection Y. You see, this time around, the symbol of intersection is turning the one for union upside down. It's like a cup turned upside down. That is the symbol for intersection. You can see the difference between the symbol for union and the symbol for intersection. The intersection consists of all elements common to sets A and Y, I mean X and Y. The intersection consists of all elements common to the set X and the set Y. For example, if X is the set of students studying mathematics and Y is the set of the students, Y is the set of students studying physics. The intersection of X and Y is the set of students studying both mathematics and physics. Students studying both mathematics and physics will form the intersection of the two sets. Some of these ideas will be clearer by the time we treat Venn diagrams. Also, if A is equal to the set 1, 2, 3 and B is equal to the set 2, 3, 4, 5, then A intersection B is the set 1, 2, 3 intersection 2, 3, 4, 5, which gives you the set 2, 3. What do you observe? These are the elements that are common to the two sets. Look at this set 2, 3. Look at this set 2, 3. These are the elements that are common to the two sets. Those common elements appear in the intersection. So the intersection of set A and set B as given is given by the set 2, 3. You should also note that A intersection B is a subset of A and B. That is, A intersection B is contained in A and A intersection B is contained in B. Yes. 2, 3 is in set A. 2, 3 is in set B. Now, the next area we are going to look into is the use of Venn diagrams. I thank all of you for listening, taking your notes. May God bless all of you in Jesus' name. Amen.